Dear students, I have selected those PYQs in which there is some concept to be understood clearly. Now, this is one such question. Now, as you know, in a cell, when a cell is connected to a circuit, in fact, here is the simplest circuit. The cell has EMF, the internal resistance, and the external resistance. Now, first of all, what is internal resistance? We say a cell has an electrolyte. The flow of charge carriers through the electrolyte faces some hindrance. That hindrance is internal resistance of the cell. Then external resistance, rest of the circuit. When the charge carriers flow through rest of the circuit, that is external to the cell, then whatever hindrance it experiences, that is called external resistance. Now, in this question, you can see there is a combination of three identical cells. Remember, now this word identical is important. Three identical cells. Cells same in all respects. So, going by this instruction, I draw the diagram. There are three cells, cell number 1, cell number 2, cell number 3, all identical, connected to some external resistance, maybe, let us say R. Since the cells are identical, that implies each cell has same internal resistance. If I call it E1, an internal resistance R1, E1 is the EMF, R1 is the internal resistance of one cell. So the second cell also has E1, R1, third cell also has E1, R1. So three identical cells. Now this graph is drawn over this combination. So whenever you get a question, especially in electricity, you must first make the circuit diagram, because circuit diagram holds the key to the solution. So the first thing here you can notice, the three cells, suppose together, are able to drive a current I1. So what will be the Kirchhoff's law giving us? Now I start from here and complete the circle, complete the loop. So starting from here, I find the current is flowing in this direction. So as I told you, whenever there is a cell and the internal resistance, let us present them separately. It means the cells will be presented like this. Here is the cell with EMF E1, internal resistance R1. Another cell, EMF E1, internal resistance R1. Yet another cell, EMF E1, internal resistance R1. And all this connected to an external resistance of R ohm. Now, suppose a current I is flowing, which has been shown here, current I1 is flowing. So the first thing we do is, since this is the potential difference, or you may say the EMF measured in volt. So let me first of all write down how is the potential difference across this internal resistance. So that will be just current into resistance. So it would be, the potential difference across this would be I1 R1. Across this also it would be I1 R1, and here also it is I1 R1. So now, and across this you have the potential difference I into R, I1 into R. So there it is. Now I have converted the same circuit only in terms of potential drops and EMFs. Now what does Kirchhoff's voltage law say? Kirchhoff's voltage law says that algebraic sum of all the EMFs EMFs and the potential drops must be 0 when we complete the loop. That is, we started from somewhere and we come back to end at the same place. So let me start from here. Now in this branch you find that the current is going like this. Current is going like this. Throughout the branch I have marked the same current. It's a single branch, so the current is same through every component. So first thing we note is that we are going in the direction of current. Going in the direction of current means going from higher potential to lower potential. Going from higher potential to lower potential. So we are going down. Therefore, I can write minus I1 R1. We have reached here. In going from here to here, you are going from lower, that is negative terminal, to the higher potential terminal, that is positive terminal. So you are going up by E1. Same thing here, you are going low, I1 R1, and here you are going up, so plus E1. Again, here you are going low, that is I1 R1, and here you are going up, that is plus E1. In going from here to here, again you are going in the same direction as the current, that means you are going from higher to lower. So going down means going negative. So that is minus I1 R, and you have come back to the same place, so it is 0. So this is how we have applied Kirchhoff's voltage law in this entire loop. Now just see what all things we can add. E1, E1 and E1. So that makes it 3 E1. Now 1, 2, 3. So that makes 3 times I1 R1. And then it is I1 R. So that is I1 into R. Now remember, this entire circuit can be seen as a single cell. A single cell which I can represent like this. Instead of the 3 cells, I can write, or I can represent it by a single cell whose EMF is 3 E1 and internal resistance is 3 times R1. That's it. Even otherwise, you can notice the 3 internal resistances R1, R1, R1. They are in series. So total 3 R1 is the total resistance, total internal resistance. Now look at the rest of the circuit. It has an external resistance. It has an external resistance R, and the current flowing thereby is I1. So now this graph that has been given is for this circuit, a combination of 3 identical cells connected across an external resistance R. What was the graph? The graph was like this. The graph given is like this. So the terminal potential difference, that means if I connect a voltmeter across it, I am going to get the terminal potential difference, which I am plotting here. And if I connect an ammeter over here, I am going to get the current. So ammeter will be connected like this and voltmeter would be connected like this. With the positive terminal, there should be positive of the ammeter, and with the positive terminal of the battery, there should be positive terminal of the voltmeter. So we are going to read these two and plot over here. So on doing so, that is on plotting current versus voltage, we are getting a graph like this. And in this graph, the marking given is, it is 6 volt and it is 1 ampere. Now, how do we read this graph? Firstly, you see the maximum possible potential difference across the terminals of the cell is 6 volt. Maximum possible potential difference. Now, by definition, for any cell, the maximum possible potential difference, that is 6 volt. It means I can write 3 E1 minus 3 I1 R1 equal to V maximum. Remember, when the potential difference is maximum, you see the current is 0. That means if the current is 0, this should become 0. This should become 0. Which means the maximum potential difference is actually 3 times E1. And how much is the maximum possible potential difference here in this circuit? It is 6 volt. This clearly implies the EMF of a single cell is 6 by 3, which means 2 volt. EMF of a single cell is 2 volt. Now, in a similar way, we interpret this reading. When will the current, our question is 3 E1 minus 3 I1 R1 equal to V. This is the terminal potential difference, that is equal to, I call it as terminal potential difference, which is read by this voltmeter. Now remember here, along this graph, along this axis, we have plotted the terminal potential difference. So when the terminal potential difference is 0, then what is the current? That means when the terminal potential difference is 0, what is the current? I say the current should be 3 E1 minus 3 I1 R1. It should be like this, which clearly means since 3 E1 is already 2 volt, we have noted. So that is 3 into 2, that is 6, and here it is 3 I1 R1. Now, as you see, the current in this case is given to be 1 ampere. Current in this case is given to be 1 ampere. So, this is 1 ampere, and therefore R1 comes out to be 2 ohm. Have a look at the graph once more. See, when the terminal potential difference is 0, then the current is 1 ampere, and that is what we have used here. When the terminal potential difference is 0, then the current is 1 ampere. So on writing 1 ampere, you are getting R1 as 2 ohm. So in this way, applying the concept of internal resistance and the definition of electromotive force, EMF, we have solved this question. Just to revise, let me tell you, terminal potential difference is the potential difference across the terminals of a cell, which can be measured directly by connecting across the terminals of the cell, right? And what is EMF? So in this we have used a particular definition of EMF, and what is that? We say EMF is the maximum possible terminal potential difference across a cell. And when is the terminal potential difference across a cell maximum? We say when the cell is not sending any current in the external circuit. That means when the current I1 becomes 0. So if the current I1 becomes 0, then the terminal potential difference is just 3 E1, whose value is given to be 6, and therefore each cell has a terminal potential difference of 6 by 3, that is 2 volt. Thank you.